here. In module number 2, which is the security and client access module, we're going to talk about all the basic aspects of security when it comes to wireless technology, right? We'll take a look at the different components of wireless security, WPA2, WPA, how we provide guest access, the extensible authentication protocol, 802.1x, which is a very important concept, especially for using back-end authentication like Radius or TACX, EAP authentication, the extensible authentication protocol framework, and then we'll wrap up the lesson or the module by talking about native operating systems and how those native operating systems handle wireless connectivity, right? Handheld devices, PDAs, smart devices, and whatnot. So that's what our focus is in this particular module. It's a relatively short module. We shouldn't have any problems kind of making it through this particular module before we wrap up for the day here. But let's go ahead and get started. All right. Now, in lesson number 1, we know that security is a big concern in wireless networks. It's particularly important in wireless networks because radio signals kind of are sent out everywhere, right? To the edge of the building, even beyond the building, into maybe areas where I don't want somebody to be able to see that signal. So an attacker on the outside of the enterprise perimeter, or even somebody internally that might want to gain access to that signal, it's a relatively simple concept, at least simpler than trying to capture data traversing over a fiber optic cable or a twisted pair Ethernet cable. So in this particular lesson, we're going to talk about Wi-Fi security issues. We're going to describe the need for authentication and encryption in our wireless networks, talk about different key management techniques that are used for authentication and encryption, and really go into all the fundamental security concepts that are very important to understand when it comes to wireless communication. This is much more practical than what we've seen over the first module, where we were talking about all the theory with radio frequency spectrum and modulation and whatnot. This is applicable in a practical sense. So I think Mike and Tiju, you guys will have a much better time applying, or a much easier time applying these concepts to what you guys have to do on a daily basis. All right. Unlike the LAN, the wireless LAN doesn't really have specific boundaries. I mean, that's obvious, right? So vulnerabilities are going to exist both inside and potentially outside the building, unless you're really focusing your BSAs and your extended service sets to exclude those external perimeters. Because the popularity of Wi-Fi is so prevalent now, it's the low cost of deployment, it's easy to obtain devices, it's a fairly well-known standard. I mean, it's based on several different standards, but they're all very well known. So there are several different types of open air type of attacks that you can see in a wireless environment. Some of them are spoofing attacks, some of them are man-in-the-middle attacks, some of them are denial of service attacks. For example, maybe RF jamming or an RF denial of service attack, where you just basically use a jamming transmitter like a microwave or a cordless phone with high duty cycles and high noise to jam a particular signal. It's very, very difficult to mitigate that. The only way really is to use radio resource management and move off of the frequencies that are being jammed up. SSID broadcasting can open you up to additional vulnerabilities, right? It's a very typical thing to do to advertise your service set ID so that people can connect. But that becomes another piece of information that the attacker doesn't necessarily have to guess. So you can hide or obfuscate the SSID within the beacons by simply disabling SSID broadcasting. That's going to overcome passive sniffing, and we won't be able to see these SSIDs or discover the SSIDs by simply observing probe responses from the clients. Address spoofing, another concern in wireless networks. MAC addresses, IP addresses. It's still providing connectivity to a network, so these are the concerns that we have. Man-in-the-middle attacks, where the attacker will insert itself into the conversation and act as a client or act as an access point to gain security credentials, obtain information, maybe a security key, and so on. And then we also have rogue networks to capture maybe login accounts or harvesting IDs, credit card information, and so on. We see this a lot in the commercial space with point of sale systems and so on, where point of sale systems are used for point of sale transactions, but they're based on wireless technology, but they're not secured, so we see information being stolen. I mean, think about it for a second. Just a rogue, from the perspective of a rogue AP. How many people do you think that you could get to connect and even provide some private information if you went to an airport and turned on a hotspot and named that hotspot airport Wi-Fi, or something specific to that particular environment, or even duplicated the SSID that was being provided by the airport? It would be, if you did it fairly well, you had a splash page and welcome to the Denver airport, and here's some of the places you can go see, and by the way, if you want to get access to special bandwidth or whatever, create an account and log in, and you can capture all kinds of information. And most people would fall for that, right? Now, that's a very difficult thing to mitigate. You have to have a pretty active security network to be able to do that. All right. Two primary facilities for securing a wireless LAN. One is authentication, identifying the users and who they are, and the other is encryption. Authentication has been used for a very, very long time. We've used it well before websites or wireless even existed, and it's basically the process of requiring a user to present some identification, whether it's a security key or multi-factor authentication or whatnot, to be able to identify them to permit them access to a specific resource. Now, the access component is what we define as authorization, and that can be a secondary component of authentication. But basically the goal here is I simply want to prove the identity of the individual that's connecting to the system. Encryption is a mechanism that's used to protect the data that's flowing over the actual data pathway. Encryption is accomplished by using encryption standards like DES or triple DES or AES, and locking the data down with keys to hide the data. We don't really get into the specifics of encryption protocols in this class. That's something that you cover in the CCNA security. Current security standards, unless it's like an open type of network or an open environment, pretty much require both authentication and encryption to protect the users and the data, etc. So let's take a look at authentication kind of more specifically. There are multiple ways of authenticating in a network. All right. Now, there is this concept of what we call multi-factor authentication, where we can identify multiple facets of a user. So something you know, something you are, something you have, and so on. Or it can be a very basic authentication process. But in the end, authentication is basically the process of finding out whether something is exactly what it appears to be. In a wireless network, we want to prove the identity of the person, right? Or the device that's trying to gain access to the network. Providing an identity is difficult because it's rarely possible to physically identify the person that's trying to connect. Because we don't have biometrics or something that's physically going to allow us to identify that person. There are different approaches for human authentication. Something that like a password. This is kind of really the most common method. Or something that you have, like a smart card, or something that you are, like biometrics, like a fingerprint, or retina scan or vein scanner or whatever it might be. All right, give me 1 second, guys. My batteries are dying on my microphone. I'll be right back. I'm going to replace those real quick, and then we'll continue on.
What are they calling, Dad?
Now, standard wireless systems don't really allow us to incorporate all of these different methods for authentication, but we can use extensible authentication methods to include or incorporate these functions in our authentication process. And we'll see that as we kind of go through this lesson here. The other option is, do I authenticate the device or do I authenticate the user? And there are certainly options for that. Typically, we're authenticating the device itself. We're not necessarily authenticating the user, but we can incorporate technologies like ICE, Cisco's Identity Services Engine, which will allow us to incorporate not only device authentication and profiling and posture assessments and whatnot, but also to identify the user. The authentication methods that were described previously, right, these apply to human or user-based authentication. Authenticating the device is a method that's used to access the network, or as a method, I suppose, I should say, is also commonly used. A machine can be authenticated by using some sort of signature that's based on a specific hardware characteristics of that characteristic of that machine. The machine can perform complex algorithmic calculations, and it can exchange messages. So we can use things like MAC addresses and other hardware-based authentication methods to identify the device. There is a limitation, though, right? The limitation of device authentication is that it does not authenticate the person who makes the connection. The same authentication process occurs whether the device is being used by Bob, by Sally, or whomever. Whether the infrastructure authenticates a device or its user, the process that we use occurs when connectivity to the network is possible. That means starting from the switch to the AP at layer 2. So authentication can occur deeper in the network, but typically we're going to try and do it as close to the edge of the network as possible. All right? Encryption, well, I think everybody here pretty much understands what encryption represents in the form of a network, but we will talk about different encryption techniques quite a bit. Wireless networks need to achieve a certain level of privacy, and in order to achieve privacy, we have to hide the data. Who's the owner of that data? How's that data being managed? How is it being transmitted? And if anybody sees that data or the data stream, are they going to be able to interpret what that data is? We want to basically prevent eavesdroppers from being able to access the data. So encryption can be defined essentially as the process where plain text information gets transformed using a cipher, some sort of specific process, to produce the result that is only readable to the intended participant, right? And that involves the use of an encryption key, an encryption algorithm, and so on. We'll get into that in detail as we move through the lesson here. There are several encryption methods that exist in the wireless world. WEP, Wired Equivalent Privacy, that uses a shared key where both sides have the same key essentially. It's not really considered to be too secure these days, and we don't use it too much these days, but excuse me, there are other options, right? TKIP. That's a suite of algorithms. It's actually not an encryption protocol itself. TKIP stands for the Temporal Key Integrity Protocol. And it's used in the 802.11 space, designed by the 802.11i workgroup and part of the Wi-Fi Alliance as an interim solution to kind of replace WEP without requiring the replacement of hardware. There was as we moved from WEP over to WPA and then WPA2, there was some requirements to change out some hardware. So this was kind of an interim solution. It wasn't an encryption protocol in and of itself, right? WEP, the Wired Equivalent Privacy, just like AES, not technically an encryption protocol. AES is just a standard. The actual encryption process in AES is the Reindel algorithm. In WEP, it's the RC4 algorithm, which was developed by Ron Rivest way back in the day. But the problem with WEP was that the keys were not secured. And they could be derived or otherwise discovered through various means and various processes. So what we do, we add a TKIP, which was an algorithms, a set of algorithms that applied to both WEP and WPA, Wi-Fi protected access, to enhance the security. It actually isn't an encryption process, it's a key management process. That's why it's called the Temporal Key Integrity Protocol. So we're trying to protect the integrity of the keys that are used as part of the process. In any encryption process, the algorithm is really not, I mean, there are certain design elements in certain algorithms that make them inherently more secure, but everybody knows how these algorithms function. It's the crypto variable that needs to be hidden and secret and maintained. And then we see AES, which is an encryption algorithm or an encryption specification, uses the Rindell algorithm that provides for longer key space, which increases the work factor, of course, for any kind of cryptanalysis, and it's used in most wireless LAN security mechanisms today. When it comes to security, there's also another concept that's important to understand, and that is whether we're using some sort of symmetric encryption process or an asymmetric encryption process. Quite simply, a symmetric encryption process is a process in which the crypto variable, that is the key, that is used to encrypt the data is the same crypto variable that's used to decrypt the data. Okay? Typically, 99% of the time, that's what we're going to use for bulk encryption. We're not going to use it usually for authentication. We're not going to use it for a key exchange process. We're going to use that for bulk encryption. Asymmetric encryption, which is typically called the public key infrastructure, or it's based on the public key infrastructure. We have a key that's used to perform the encryption, and then we have a different key that's used to perform the decryption. Now, these keys are paired together. One is a public key, one is a private key, meaning the private key is something that we don't share with anybody, we only know ourselves and it's never shared, versus the public key, which is shared readily. Depending on what our goal is, will depend on how this asymmetric process is used. If my goal is authentication, non-repudiation of origin, digital signage, signing, I should say, not digital signage, but digital signing, I'm going to use a private key to encrypt variables or data, and then the receiver will use a public key to decrypt that information. If my goal is confidentiality and hiding information, oh, and by the way, in that previous example, the sender uses their private key, the receiver uses the sender's public key to do the decryption. In the second scenario, where I'm trying to provide actual physical encryption for the purposes of hiding information, the sender will use the public key of the receiver, and the only way that you can decrypt that data then is by using the private key of the receiver, the corresponding private key of the receiver. So there's a couple of different ways that we can integrate this asymmetric process. We'll take a look at how the asymmetric process is used for key exchange and how it's used for authentication and so on in the wireless environment. Although this is not a security class per se, we do get into some of those security concepts. Whether keys are used to authenticate users or to encrypt data, they are the secret values that we base the security on, right? If a key is compromised, it doesn't matter how strong the algorithm is or how strong the process is in authentication and encryption, we will be compromised. A key can be common to several users. That would be an example where you have WEP, right? Wired equivalent privacy. We understand what the downside of that process is, right? The downside of that process is that that key is probably well known and can be easily exchanged. Keys can be used for authentication, where a user has a key to simply identify their identity, something they know. It can be used for encryption only, where I'm not really concerned about authenticating the user, but I do want to make sure that the data that's being exchanged is hidden. Or it can be used for both. And that's typically what we do, right? We talked about how in most wireless systems today, we focus on applying both of those principles. The advantage of a common key system is its simplicity. Everyone kind of uses the same algorithm, they use the same key, but the risk is its simplicity. Anyone who has the key can capture that information, and those keys can be duplicated and shared. So it's not something that we tend to utilize today too much. To provide more security in an environment, an individual key can be defined for each user. The key is individual from the beginning. That implies, of course, that the infrastructure has to have a way of storing, managing those keys and distributing those keys, maybe a central authentication server or something like that. Or the key is common at first to do that initial connection, but then that common key is used to create a second key that's used by the unique user. This is how most VPNs work, right? If you're not using RSA. You'll have a pre-shared key that allows you to authenticate the peers, and then use something called the Diffie-Hellman key exchange process to generate and share the shared secret key information on the fly. Individual keys cannot be used to encrypt, broadcast, and multicast messages because nobody would, well, not everybody would be able to decrypt that information, right? If the recipient has, well, let me just say this. If wireless networks that use a common key to encrypt, if I have broadcast traffic or multicast messages that need to be generated and transmitted, that's going to be done with a common key. It would have to be done with a common key. Individual keys are for unicast frames and so on. All right, now this is a very, very high level discussion, very, very short lesson, just kind of an introduction to some of these high level concepts. So we talked about Wi-Fi networks and how we can extend the LAN beyond physical boundaries because of the nature of transmitting wireless signals. Talked about basic concepts of encryption and authentication. What we're going to do now is we're going to get into lesson number 2. And lesson number 2 is specifically looking at 802.11 security concepts and how those work in our environment.